Welcome back to the lab. Welcome back to EEforEveryone. Today I'm really excited. I'm really excited because we are going to be designing our linear MOSFET driver. Not a MOSFET driver, a linear MOSFET driver. Now, there's a couple things that I think need to be explained because on the surface, those sound kind of like the same thing. One of them's a MOSFET, the other one's a MOSFET. They're both being driven. Why is this special? Why do we need to talk about this? Well, the reason why is kind of buried. And that's because there's a typical application for nearly every MOSFET, nearly every N-channel MOSFET on the market. And most of these FETs, most of these transistors are optimized for one purpose and one purpose alone, and that is switching. Okay? These transistors are typically voltage controlled. Well, they are. That's MOSFETs. That's their nature. They're voltage controlled transistors. And these voltage controlled transistors, they're designed to switch very efficiently. So when you're building them for something like a hot swap controller, a switch mode power supply, when you're building a logic circuit, you want these things to turn on and off as fast as possible. Infinitely fast transitions are ideal. And that's why whenever you're building a switch mode power supply or one of those other circuits, that's why NFETs are pretty great. They're usually a pretty good choice. So those switching applications, they all really have one thing in common. Switching. That means that most of the time they're either completely on or completely off. And that means that there's never a lot of current flowing when there's a lot of voltage across the part. It's never really designed to dissipate power for a significant amount of time. That's not what it's optimized for. It's meant to go full on where there's a lot of current and low voltage, or full off where there's a lot of voltage and no current. And the only time you're really burning significant power, ideally, is in that transition, while that part transitions from on to off or off to on. And that's why they're made to switch so fast, because that minimizes, well, one of the reasons, because it minimizes power dissipation in that part and therefore increases the efficiency of your design as a whole. The more ideal your ideal switch is, the better it's going to be. So because of that, MOSFET dies, they're typically shrunk really small, right? Parasitic capacitances will make it switch slower. But that means that if it really needs to burn some power, if you really need that FET to burn some power, it's kind of all in one spot and it's hard to get the heat out. So because of that, there's a lot of MOSFET gate drivers out there, and these MOSFET gate drivers are made to complement those transistors, right? They'll dump an amp, 2.5 amps, 5 amps of current as a surge just to whip that transistor from off to on as fast as possible, or on to off as fast as possible. They usually have a binary input. It's either on or off, and they'll have maybe some fault monitoring or something, but really, they're made for on or off. They're not made for part way on. That's just not really what they're made for. And now I suppose we could build a switch mode electronic load. We could have an inductor and switch the FET, but then we'd have some ripple. Like by design, our current source would need to have ripple in order to make it switched. That's not really what I want to do, especially for this one. Now, there may come a day down the road where we have a multi-stage, where we have some current sources in parallel, and perhaps our highest voltage, highest power one would be switch mode, because if you're operating at the kilowatt range, maybe you don't care about a few watts of ripple. If you're operating at 50 amps, maybe you don't care about half an amp of ripple. So maybe that's a way that we can get the power cranked up beyond what we'd feel comfortable burning in a FET. But that's not today. Linear operation is, and forever will be, the king for low noise, low ripple loads or power supplies. There's no way around it. They are not efficient, but they can be rock solid, no ripple, super clean. It's pretty easy, relatively easy, to make a low noise, low ripple power supply when it's linear. So you picking up on what I'm putting down here, basically most FETs are built for switching and burning very little power in the part and turning them on and off as fast as possible. But what we're going to do is we're going to find a MOSFET that is optimized for burning steady state powers. It's going to have a bigger gate. It's going to have, as I like to say, a big hunk of glass in there, that silicon wafer, a relatively large wafer, a relatively large gate capacitance, and it's built to sustain this linear operation. burning significant power for an extended period of time. And in order to do that, we need to build a gate driver that not only can drive to those linear voltage levels required to use it like a voltage controlled resistor, it also needs to handle the gate capacitance that we expect to see. And that means that we'll be able to use a FET as a variable resistor instead of a switch. So the MOSFET. We left off saying that a linear MOSFET is what we are seeking. That might be a bit of a misnomer, or maybe it's a part of a branding thing, but all MOSFETs do have a linear region, just most of them aren't optimized to operate there for an extended period of time. So we're seeking a transistor that has a larger ohmic region or linear region. So basically it's designed to operate in that. It extends the range a little bit. And that means that the internal resistance will change less for each unit of voltage applied at the gate, making the device easier to control with an OpAmp circuit like what we're trying to do. And that's perfect. So I found a part from Ixis, and it's a part of their linear L2 series. This component should allow us to burn about 300 watts maximum, 90 volts across it, and 10 amps DC steady state. So you either hit the power limit or the voltage limit or the current limit. Whichever one comes first, we need to enforce that. But that's not bad for one part, right? That's not bad for one MOSFET. The plan, of course, is to eventually put multiple of those in series, or maybe a super high precision, low power one, and then this like medium power stage in the middle, and maybe a high power stage. And since it's a current source, basically you just put them in parallel and you can sync some current through some and the rest of the current through some others. So that's pretty cool. Not to get distracted though, let's focus back on this MOSFET. The critical thing that this MOSFET is designed for really shows up in two of the characteristic curves. And those curves are the gate charge curve and the safe operating area curve. Just looking at where that safe operating area curve goes, it's pretty obvious this FET is something special, because you don't usually see 300 watts of power burned in a MOSFET as a part of their steady state, this is totally fine, don't even worry about it type of rating. That's not normal. And the gate charge is equally insane. About 450 nanocoulombs of charge when going up to 15 volts. That's somewhere between 10 nanofarads and 30 nanofarads of gate capacitance, depending on where and how you want to measure. So that's quite a lot. That's more than every other FET I've worked with. The big deal about driving a part like this, you need to remember what we're driving it with, right? It's an OpAmp. It looks a lot like this. And basically what that means is there's a limited amount of output capacitance that we can drive. These parts become a little unstable. And by a little unstable, I mean very unstable. They start to oscillate if you put too much capacitance on the output. And that's not great. So we're going to need to think about that. We're going to need to make sure that the amount of gate capacitance in this FET isn't going to make the OpAmp unstable, because if we start to ring, that's not going to look good. That's not going to be that nice, clean electronic load that we're going for. That'll be a noisy, hot piece of garbage. Probably all of those things. It will be garbage, it will be hot, and it will be terrible. So we better not do that. Better not have that oscillation. Okay, so I got a little further than in this design off camera, and started looking at the OP07 like you just saw. It's a pretty great part, but even great parts have limits. And basically the quantity of capacitance that part can drive is about 500 picofarads or 0.5 nanofarads. So any more capacitance than that, if you connect it straight to the output of the OpAmp, it'll start to ring. It'll start to oscillate. And our MOSFET, just by itself, no extra capacitance, no parasitics over PCB, somewhere between 20 and 60 times more capacitance on that gate than the OpAmp can drive. Okay, now we have a problem. We need to do some optimization, but what are we going to do? Okay, so we have a couple options on how to work with this issue, with this gate capacitance exceeding the output capacitance that we can drive with our OpAmp. The easiest way to work around this is just adding a series resistor between our gate capacitance and the OpAmp. Great, that can keep it stable. There is a resistance that will keep our OpAmp stable that will also drive the gate capacitance, but now we've added an RC time constant. We've added a low pass filter, which means there'll be a delay. There'll be a delay between when our op-amp hits a set point and when our FET responds. And that delay, if there's too much, can make our control loop unstable. That is not great. That's actually quite bad. Yeah, and also it will limit our maximum slew rate. It will limit our maximum amps per microsecond because it limits our volts per microsecond at the gate of the FET. So both of those things aren't great. That's not really a great solution. Yeah, so the second option becomes, let's find a way to drive the gate that is less sensitive to that output capacitance. Before we do that, though, let's hop into LT-Spice and let's just play around a little bit. Let's see if we can get this thing to show its instability. Let's see if we can get the OP07 to oscillate. And basically the way that I've done that is I've added a step command that will step our gate capacitance from 25 nanofarads up to 100 nanofarads with 25 nanofarad increments. So it should go from unstable to very, very unstable if this is working right. And the R gate is going to go from 10 ohms up to 410. So we should see it go from unstable to rock solid stable if this is functioning correctly. Gonna hit run here. And okay, it looks like this FET model, or this op-amp model doesn't have that instability modeled. So that's a shame. It did finish all the runs. If we come in here, you can see there's a lot of graphs on top of one another, but it's really just not modeling that effect of the OP07. That's okay. It's okay that our simulation doesn't model it. That's good to know, because what that tells us is that this is real. Like, just because it doesn't show up in the simulation doesn't mean that this effect won't happen. This is real. This happens. I've seen it. I've debugged it. This is real. Do not ignore this when you're designing an op-amp circuit. But it means that we need to be extra careful about our analysis because the simulation won't uncover it. If we really design this issue in, we know that LT-Spice isn't modeling that for this op-amp, and that's just going to be a problem. We might see that on the bench, even if we don't see it in LT-Spice. We need to remember that. I have another simulation prepared, and we're going to switch over to that one. So this is, if you look in the description, the video description, you'll see that we have this simulation linked, and I believe this is the whole thing. We don't really have a compensator here. We're just testing that output. And I'll zoom full. Yeah, okay. So basically what we have is just to show you around the simulation, I didn't do a great job of showing you that before. I'll walk you through it right now. And basically what we have is this is modeling the gate capacitance of our FET. We're just adding in the gate capacitance as a capacitor. We're not really looking at the rest of this. We just want to make sure that we can drive the gate. I've still left a little gate resistor in here. 1 milliohm is basically, that's the trace. And what we've just added is this discrete BJT voltage follower. And why is that important, right? So we've got a load over here. Think about this like a complex load, or like an impedance rather than a resistance and a capacitance. So that we have a complex impedance hanging off of this BJT voltage follower. We've got basically a gate resistor. So when we sync in source current, that will limit the peak current going in, that 1 ohm resistor. Then we've got this complementary BJT pair that's driven by this BJT pair. So basically what we have is we have the gain of these transistors, and that's separating the output of our op-amp from the capacitance. So if you reflect that back as an amplifier, you're seeing, well, basically you don't see any effect from that capacitance because the current is coming from these BJTs instead of our op-amp. It drives a set point, and then that BJT follower does its best to keep up. Pretty perfect. So it's adding a bunch of gain, it's separating the capacitance from the op-amp, and it should keep the op-amp stable while still driving the same output waveform. But it's one thing to say it and another thing to see it, so let's hit run. So looking at the output of our op-amp, you can see the set point that we intend to drive, And now we can see the output waveform as well. And what I would expect to see is just a little bit of delay from input to output. That's pretty darn close, though. That's pretty darn close. Yep. It's slightly different. Slightly different. But it's driving a whole whack ton of current into the gate of our part. Let's plot the current. Look at that. So as our gate capacitance is changing, sometimes we need to drive a milliamp, sometimes we need to drive 5 milliamps. But regardless of what is required, that BJT voltage follower drives whatever current is necessary into the gate. Perfect. That is perfect. That's exactly what we would want to see. But more importantly, if we look at the current out of our MOSFET, we can see that it's microamps. There's almost no current flowing into those BJTs, as we would expect, as we would desire. If there's no significant current coming out of our OpAmp, that's confirming that it has basically no part in charging and discharging that capacitor. That's coming from the much beefier discrete BJTs. In other words, one could say that adding the discrete BJT voltage follower just annihilated, absolutely annihilated the effect of gate charge and gate capacitance for this OpAmp in this system. Basically, heck yeah, let's keep this moving forward. I feel like I've been talking a lot about what is a pretty simple circuit, so let's start to wrap this up. But there's one more thing that I want to talk about. There's one more thing that I need to acknowledge here. A circuit like this BJT voltage follower, is very similar to what you might find in an OpAmp or in an integrated circuit. But there's one critical difference. And that difference is that these are discrete components. These are not built on the same wafer. These are not complementary pairs. And what that means functionally is that their gains, their forward voltages, their temperature effects, those types of parasitic effects aren't going to be matched. They're not going to be perfectly matched. And that means that there will very, very likely be a DC offset between the input and the output of this voltage follower. That is likely. Highly probable, in fact. But for our system, since we have the compensator, it doesn't really matter. Right? A fixed DC offset will be accounted for by the integrator. That'll just crush it, right? So when you boot, there might be a small moment where the FET behaves slightly different than you would expect. Maybe it's 10 millivolts, maybe it's 100, maybe it's a volt. But we've got plus or minus 15 volts to play with. There's plenty of room here to compensate for that error. And if worst comes to worst, what we can do is we can just add a series resistor that's maybe 100 ohms, 50 ohms, tie it straight to the gate from the output of our OpAmp, and just accept that the transient response will not be sufficient. This isn't meant to be a one and done slam dunk. I want to learn something with you, and I want you to learn something with me. So let's make this calculated risk to do something that I believe will expose some non-idealities of building a discrete transistor circuit with unmatched transistors and unmatched discrete transistors rather than like matched pairs or other types of transistor configurations that might minimize that error, and just see what happens. Let's explore this together. Like I said, I don't think this will kill our design. I don't even think it'll really slow it down. Our compensator is basically built for this DC offset, right? There's a DC offset that will be the operating point of our FET, and that's going to be like 4 or 5 volts, and we can account for that just fine. What's another 100 millivolts? I think it's fantastic. Rarely have I had an opportunity to design a BJT buffer into a circuit like this and actually have a justification for it. So I am excited to do something that's just a little weird, and I think it'll work out just fine. That's fantastic. If you like this video and you can't wait for more like this, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we will be designing the over voltage and over current protection for this electronic load. We will be kind of getting this architecture a little more tangible, where you're going to be able to see the general construction of that high voltage portion of the design, and that's pretty exciting. I can't wait. If you want to support the channel, consider checking out our Patreon page linked in the description. Down there, you'll also find links to this LT Spice simulation. It really helps us out a lot, so thank you. Thank you to those that have decided to become a member. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye.